Hey everyone, this is Professor Mankowski. And in this video, we're going to be talking about section 3-2, which is measures of variation. Now, variation has to do with what we call the dispersion of the data set. And by dispersion, we mean how widely dispersed are the observations from the mean of the data set. If a data set has a lot of dispersion, it means that the individual data values are scattered very far apart from the mean. And if the data set doesn't have a high amount of dispersion, it means that those observations are located very closely oriented around the mean of the data set. Now, variation or variance is also where our formulas and statistics begin to get rather complex pretty quickly. So what we're going to do is we're going to talk conceptually about the background of the variance, what it's doing, why we want to measure it, and how it can be helpful. And then very slowly, we're going to get into the mathematical end of it. And to begin with, let's consider two different data sets. We have the data set on top, the data set on the bottom. And if you were a gambling person and you were going to put all your chips down and pick one data set and guess which number came next, would you want to pick the data set on the top to bet on, or would you want to bet on the data set on the bottom? Which one would you choose? Now, most of us would probably say that we wanted to use the data set on the top because it looks a lot more predictable. We see that the number 1 keeps coming up over and over in the data set. And even if the data set changes to a different number, like a 3 or a 2, it always seems to come straight back to 1. So we would guess that the next number is going to be a 1, right where that question mark is. For that reason, we would say that the data set on the top seems to be a lot more stable, doesn't it? Now, the data set on the bottom is fluctuating by a lot more. It's going up and down by leaps and bounds, and it'll be really difficult to try to guess which number comes next. So when we're thinking about the reason why we prefer the data set on the top, it's because it seems to have a lower variance. And that means the numbers are varying by just a small amount from one observation to the next. So if we're thinking of what's synonymous with a low variance, we would probably say it would be a very stable data set because there's not a lot of fluctuation in it. And it's also very predictable. If we had to base a forecast or a projection on a data set that was very stable, we would probably say it's pretty easy to predict what's going to happen next. And that means if we were actually doing a forecast equation based on a data set like the one on the top, it would probably be very risk-free. So then let's talk about what it would be like if we were working with a data set that had a high variance. Well, it probably wouldn't be described as a stable data set, but a more unstable data set. And instead of predictable, we would say it's very unpredictable. Because if we were doing economics or finance, we had to do a projection or forecast, and we're basing it on a data set like the one on the bottom, it's going to be very hard to predict and get the next value correct, isn't it? So that would probably tell us that it's going to be a really risky forecast. So what's happening is that because the data sets can vary in their degree of stability or variance, which ultimately leads to the amount of risk that can be involved in a calculation, we have to have some way of calculating or quantifying how much variability is in a data set. Now, how do you do that? How would you quantify how much variability is in a data set? And the answer is there's 3 different ways to do it. We can calculate the range, the variance, and the standard deviation. The range is the simplest and easiest way to calculate it. It's very fast, but we're also going to find out that the range has a number of shortcomings. So pretty quickly after we start to work with the range, we're going to find out that we need something much more sophisticated to take over. That's going to bring us to the variance. The variance is definitely more complex. At the same time, though, we get much more intel on the data set when we use the variance. And variance and standard deviation are almost joined at the hip to each other. So we'll talk about exactly what's the difference between the two and when you would want to use which one under what circumstances. So to get us going, let's use a introductory example here. And it's going to be about painting a room. So we visit the paint store and we find a salesperson. we tell that salesperson that we need to get a brand of paint that dries really quickly. So they give us samples of drying times from two different paint brands, the brand A and brand B. And the captions for both of them say variance of paint in months, but we're going to pretend that's in hours just to make the example a little bit more easy to follow. So if we take a look at brand A, all the way on the far left there, it looks like somebody used the brand of paint once. They painted a room and it dried within 10 hours. Another time, room dried within 20 hours, and it looks like the highest dry time that was recorded was 60 hours. If we look at data set B on the bottom there, one instance of 25 hours that was used, a couple instances where it took 35 hours for the paint to dry, and it looks like the greatest amount of dry time was 45 hours. What I want you to think about now is if you were a professional painter, which paint would you prefer? Would you want brand A or would you want brand B, assuming that the dry time is the only difference between the brands? And the answer is brand B we would probably prefer because it's much more reliable when it comes to dry times. The dry time window is much smaller, between 25 and 45 hours, whereas the data set in brand A is much more wide. It'll dry anywhere from between 10 hours and 60 hours. So it's going to be a lot more difficult to use and properly get a fix on when the room is going to be ready to use again. Okay, so if we're thinking that it looks like brand B is more narrow compared to brand A, so brand A is much more widely dispersed than brand B is, and that's what affected the reliability factor, how can we calculate that spread outness that we're seeing? And the answer is going to be the range. So the range is going to give us the physical distance across the data set. And the data set that has the greatest physical distance must be the data set that is more widely dispersed. So to calculate out the range, we're going to get the maximum of the data set, and we're going to subtract from that the minimum of the data set. So we'll go ahead, we'll calculate the range for data set A, that's going to be 50 hours. Range for data set B is going to be 20 hours. So that means data set A is definitely much more widely dispersed than data set B. Data set A is taking up more room on the number line than data set B is. Now, the range is obviously quick and fast to calculate, but it's got some major shortcomings that are going to present a really big problem. To see what the shortcomings are, let's just work with data set A for a while here. And if we had a big shifting in the data set and we ended up with new data values, let's take a look and compare what might end up being a case, what might end up happening. And we're going to leave the original numbers for data set A on the number line. We'll write the new values in red X's on the top so we can compare both. And it looks like the red X's, our new dry times, they really changed the data set a lot. All the dry times are kind of crushed down on the left side. So the data set now just suddenly became very compact. And when we're looking at this, I want you to think of what did the range just change to? What's the new number for the range? And the answer is, it didn't change. It's exactly the same. It's still holding at 50. Now, why didn't it move? The reason it didn't move is because the lowest number is still the same and the highest number is still the same. So that's really bad for us because the implication is that all the numbers in between the lowest and the high numbers scrambled. They're all different now, but we can't detect any of that at all using the range. And that's a really big problem for us. That's bad because it means that if the range can only see two values, basically, that means it's completely oblivious to everything else in the data set. And that's what makes it the least sensitive measure of dispersion. So if we want to use something more sophisticated, we're going to have to go far beyond the range if we want to take the position of each number into account in the data set. So how do you do that? Like, how do you get more sophisticated than using the range? Our answer is going to be the variance. So the variance is going to consider the position of each individual number in the data set. And what the variance is trying to do is the variance is trying to measure the average distance between each observation and the mean of the data set. Okay, so from that, what we could tell is if the variance is very low, that must mean that the numbers are positioned very closely around the average. And I'd like to think of that picture in the elevator of all those people piled on top of each other. That kind of reminds me of what's happening in the number line, because it would mean on a number line diagram that our observations are all very closely oriented around the mean. Now, if the variance is really high, that means that the average distance between each number and the mean is very large. So the values must be very widely dispersed from the mean. And like that picture, because it has the people spread out so far, it reminds me of a data set with all the numbers scattered very far apart from the mean. Okay, so how would we calculate out the variance in this case? Okay, so to calculate the variance, we know that we're out to measure the average distance between each observation and the mean. So what I'm going to do is I'm going to start by just making a list of all the x values from that same data set. And since I know I have to take each of those values and subtract it from the mean, I'm going to go ahead, I'm just going to make a column right next to that. I'm going to just drop in my mean next to the observations to make the subtraction easier. So I'm going to come in and make a column, and I'm going to say I'm taking each x value, I'm subtracting it from the mean. I'm going to write in all those distances. And now it would seem that all I have to do is take all these numbers, add them up, divide by the total, and we're in business. But it won't work. Now, the reason why is because if we have to add up all these numbers, the negative 25 will cancel with the 25, the negative 15 will cancel with the 15, negative 5 will cancel with the 5, and we're going to end up with 0. So we can't divide 0 by a number and get anything meaningful. That means that we're going to have to do something to wipe out the negatives of the data set so that we are able to go and add everything up. What would cancel out a negative? And the answer is we could use the squaring function. So right next to the column, we're going to write in that what we're about to do is take all the numbers in the preceding column and square them. And we're going to go ahead and carry out all the squares. Now we can go ahead, we can add up all the numbers in that column, and we're going to get to 1,750. So we're going to bring that a little bit higher up on the screen. We're going to take 1,750 and we're going to divide it by, this is the part that gets a little strange, 1 less than the total number of observations. Don't worry right now about why we're subtracting 1. We're going to explain that in a couple more minutes. So let's just take a minute or two and let's summarize what's happened so far. What we did from the start was we took each x value and we subtracted each, here's our each x value. We had the mean of the data set, and we took each x value, we subtracted it from the mean, our x bar. So our formula is going to tell us right on the numerator, we're subtracting each value from the mean. When we concluded the subtraction, the next thing that we did was we squared all those differences. So in our formula, we've got a squaring function written in right here. Once we squared all the differences, we totaled the column of all the squares, and in our formula here, we've got a summation sign right there to show that we added up that whole column. And we divided by 1 less than the total number of observations. So here's our 6 minus 1. And in statistics, we call the total number of observations n. That's n because we used a sample. So when we carry out the math, we end up with 350. And that's going to be our variance. Now, we do have a symbol for variance that you have to know. That's s squared. And you have to memorize that symbol because we're going to use it almost for every calculation between now and the rest of the semester. So in the end, we found out that our variance is 350. So we finished our big complex calculation, but we had this problem because we ended up with the average square distance each value is from the mean, but that's not at all what we wanted when we started this. Now, we were trying to go and get the average distance each value was from the mean. That was our intention. And now, because we ended up with all this squaring stuff, that presents us a problem conceptually. Like, think about if you have a part-time job, you make $10 an hour. Somebody asks you, how much money do you make? Would you say I make $100 squared an hour? People would look at you a little strange. It wouldn't make much sense. If you drove 5 miles to get to the school and somebody said to you, how far did you drive to get to the school today? And you said, I drove 25 miles squared. Would you really talk like that to somebody? And you would say, no, I would just say I drove 5 miles. So we need to do something to get rid of the squared part and just make this refer to the average distance each number is from the mean. So how do you do that? Like, how do you go from the average square distance each number is from the mean to the average distance each number is from the mean? Well, what undoes a squaring function in math? And the answer to that would be a square root. So this is where we're going to introduce the standard deviation. What the standard deviation is going to do, the standard deviation has a shorthand symbol. We call it S. And the standard deviation S is going to be equal to the variance, rather the square root of the variance. When we take the square root of 350, we're going to end up with 18.7. So we're going to say our standard deviation is equal to 18.7. Now, though, we're sitting there and we're saying, okay, great, we know the standard deviation is 18.7, but what does that really, what does that number really mean to us? 18.7 hours of pain, what's this supposed to be about? So to think about what it means in layman's terms, we were talking about paint. So if we pick up that can of paint, we start reading the label, it's got all kinds of things written on the label, like, don't store this in a 200-degree furnace, don't freeze the paint, don't drink the paint for breakfast, all that crazy stuff they tell you. And they'll probably tell you somewhere in there how the average dry time of the paint is going to be, like how many hours. So for our case, they might say the average dry time of the paint, 35 hours. So here's what I want you to think of. When you're painting a room, and you let the paint dry, is the paint going to dry in exactly 35 hours to the T? Like if you're standing there, you're holding a stopwatch and it's as if 34 hours and 59 seconds, the paint is still wet, but as soon as your stopwatch rolls over 1 second more to 35 hours, it's like, boom, all the paint's immediately dry. And we would say, well, no, not really, because an average means there's going to be a little bit of fluctuation, a little bit give and take. So exactly how much fluctuation would there be around the average? And the answer is exactly 18.7 hours. So if the average paint time to dry 35 hours, we can expect that our paint will dry within about 18.7 hours of the average. Now, here's something that you can think about for just a minute. That's a really neat application of standard deviation. If you're in charge of quality control for that paint company, would you want your standard deviation to be really high or really small, really low? And the answer is we would want the standard deviation to be really low because it means low standard deviation, there's going to be very little fluctuation around the average of what actually happens in real life when you use the paint. So your customers are probably going to be happier because their experience with the paint is going to more closely match the specifications of what you tell them is going to happen when they use the paint. Okay, so let's stop and talk about why we had to keep doing n-1 from our denominator. Now, to answer that, we know more about the standard deviation now. We know more about the variance now because we just learned how to calculate them. Here's our formulas. What we didn't quite talk about much at the time was that those formulas were specifically for using a sample of data. And when we use a sample of data, we have to put in a little fudge factor into our formulas. When we're calculating variance and standard deviation off of a population, we don't have to put in the fudge factor, so our formulas are going to look a little bit different. And let's see what happens. If we use a population, there's going to be two changes in our formula. And the first is, instead of using x bar, we're going to switch over to mu because x bar stands for sample average, mu is population average. And on the denominator, n, lowercase n, more specifically, is the total number of observations in a sample. If we're using a population, we're going to switch to capital N, and we won't subtract 1. Now, if we are working with a population standard deviation, we're going to end up with the same exact formula that we had for population variance, only we're going to put it under a square root sign. Now, when we have our two formulas for population, we also have shorthand symbols for them. So the counterpart for S squared in a population is going to be what we call sigma squared. So we'll refer to the population variance very frequently as sigma squared. When we do a population standard deviation, since we're not squaring anything, we're just going to call our symbol sigma. Okay, so why, when we're doing our symbols, did we have to do this n-1 thing? Exactly why? And we can see the reason why if we take a graphical approach. So what we're going to do is, without doing any math or any computations, let's just take a look at two different scenarios here. In the scenario up on top, we're talking about the wages people earn by part-time employment. And it looks like we go from a low of $8 an hour, maybe on minimum wage in some region of the country, all the way up to $500 an hour part-time. So all of these different amounts of people working. You have people maybe that are like city workers, iron workers, unionized iron workers, working part-time, people making as much money as like $400, $500 an hour part-time. Maybe somebody's a lawyer or they're a psychiatrist, a psychologist, and they're seeing people on a part-time basis. So our variability is pretty wide. When we take a sample from that population, something really different happens. We're only going from, it looks like a low of $15 an hour up to $56 an hour. And the sample is pretty small. There's only 1, 2, 3, 4, 5, looks like about 7 people. 3, 4, 5, no, 6 people in the sample. So it's almost as if the sample is always going to turn out by definition smaller than the population. And what that means is that you're going to end up with a much more narrow variability from the sample because you don't have as many people in the sample as you do in the population. Now, this is going to turn out to be a big problem for us because remember, we're using the sample to generalize and predict stuff about the population. So if you took a sample and you wanted to use the sample variance as an estimate to generalize about the population variance, now you're in trouble because you know the sample variance is going to be very underestimated. It's much lower than the true variance. So you have to do something to inflate the sample variance to get it closer to the true value. So how do you do that? Like how do you put a fudge factor in? And in our formula, that's exactly why our sample variance has to have -1 in the denominator. Because if we shrink the denominator, we're going to make the quotient larger. That's exactly what we want because we know that the sample variance is much lower than the true variance. So the n-1 is basically an inflation factor that's going to make our sample variance look more like reality. And I hope this was helpful.